It's not an assignment sheet for this unit because there were only 2 book homeworks. You already did the first one a while ago. And homework 2 is here. Everyone get the homework for tonight. It's from the book. Okay. If you haven't yet, I'll give you another second to do it.
I need like 13 minutes.
Sorry, it's a little hard to see. Can you see it, Jackson? You alright?
I got it.
Okay. Morgan, are you good? I know, it's probably, yeah, right. Alright, so today I want to address, but the emphasis is on the fact that this is a beautiful and important. Alright, let's take a look at the integral from 0 to t of 1 over 1 plus s squared ds. And we've got a d over dt out front. So my only question is, like, are we ready to go? Look at the list. Did you copy it down? What do we need? We need it to be true that we're taking the derivative of an integral. We definitely are doing that here. This certainly looks like the fundamental theorem of calculus. Do we have the derivative being taken with respect to the same variable that appears up at the upper limit of integration? The answer is yes. And do we have a constant down here? Yeah. Yes, and 0 is a constant. So I think we're okay. And then are you thrown off by the fact that the dummy variable here is not t, but it's s instead? You're fine with it, I hope, right? It's just a dummy variable. Okay? It's just like in your sum, did you want to use k, or did you want to use I or n or something? Whatever, it doesn't matter. Okay? So I think we're ready to write down the answer. Everybody go ahead and write down the answer. I'll give you no more than 5 seconds.
I'm going to write down the answer divided by 1. I got it.
Yes, what is it? It's 1 over 1 plus, and we'll say t squared. Hopefully, again, that's not bothering anyone now. You understand what we've been saying. So that was, on this first one, softball, right? Softball. That's a direct application of the fundamental theorem of calculus. Isn't that what we said, in fact, about the fundamental theorem of calculus? That this is the d dt of the integral from 0 to t of f of s ds. Doesn't that equal f of t? That's exactly what we're doing here, right? That is exactly what we're doing here. And before we did anything else, we already had all 3 of the things we needed. It was given to us in the problem. First one easy, right? Direct, immediate application of the fundamental theorem of calculus. Let's try one that's a little bit trickier. Now, before we show you, well, I'll put it up here. Here's the next example I'd like to look at. And already, what's the issue? And we'll return to what's at the top of the slide in a second. What, of course, is the issue? Like, everything looks really good, except that's an x squared instead of an x, right? So notice that we do have a dx here. So everything looks good. But we just need to recognize that it may not be obvious at first, but that the chain rule is lurking here. If you have a u of x up here, some function of x, whether it be x squared or 5x or anything else, then keep in mind, originally, when we're looking at this, keep in mind all the stuff we've been talking about all day here. This function, if you have this function right here, can you just tell me again, this function, we'll call it capital F, say, is a function of what variable? X. So if this happens to be instead, if you plug in x squared or something like that, notice that now this is a function of x squared, right? And so it might not be obvious when you first see this problem that this is a composition of functions, but it is, right? The place where our independent variable lives is now currently occupied by another function with its own set of complexities and life story, right? So if you believe me, then we just take the derivative of this. How do we do the chain rule? I forget. Oh, yes, right. We take the derivative of this with just an x squared plugged in, like everything was fine. And the derivative of this is, of course, just by the fundamental theorem of calculus, cosine of x squared. But of course, if you stop there, you're wrong, right? Just like you're wrong when you did the chain rule back in the day, right? We still need to multiply by the derivative of the inside function. And I just need you all to see that x squared is, even though this looks complicated, the x squared is the inside function here. The outside function is this big nasty thing where we're plugging x squared into. So of course then we multiply by 2x. Okay, so it says that up here, but I just want to make sure you're understanding the notation here. So there's some function up here. So what do we get? Well, of course we get f of u, whatever, or u of x, you could say. If you want to write u of x here, you can. And then afterward times du dx. We're using Leibniz notation there. All right, but the final answer is what I have written here. Are you okay with that? You could write it as 2x cosine of x squared or something like that if you like to. However you want. Yeah. Okay. Let's add multiple more layers of complexity. I don't know if I would use the word prevalent, but present.
Like if it wasn't squared, then
Yeah.
the answer would just be f of x.
Where'd my...
That's on me, that's on me, that's on me.
Where'd it go? I'll do it again, I guess. Now remember, this constant doesn't matter. If it's 0 or 5, it doesn't matter. We just need it to appear on the bottom. So then it's just apply the fundamental theorem of calculus to this guy. That's just 3x sine x. So yeah, we're switching the limits of integration and the negative pops out, like Ashley said. I just do whatever Ashley says there. She wants an... That's our final answer. Questions, though, from Piper or anyone else? You good on that? Or? Okay. All right, we've done that problem twice now. Here, let's try a truly exciting one now. This is similar to the one I promised on the board a minute ago, right? How do we handle this situation? All right, so I need everyone just to have a moment to think, calm down, and realize that, like, maybe we can do this. Think about your wish list and how you can bring that to reality. How can we get what we want here? That was good. It wasn't a problem. All right, anyone come up with a genius move?
Oh wait, yeah, you're right.
What'd you say, huh? Yeah, let's use two integrals here. Yeah. So we're gonna break it up, and we can use whatever your favorite number is if you like. Doesn't actually matter. So we'll do that. We'll do this in a couple steps. So we'll do the integral from 2x to something. And we'll do the integral from that thing, whatever you want to choose, to x squared. And now, I don't know, what number, it doesn't matter in your work what you write, right? What number would you like to put there? As long as it's any constant of your choosing. I'm just going to put 0. But if you want to put 5 here and here, also fine, right? It doesn't matter where we break this up. This is a property of integrals that we can use, isn't it? And derivatives. We're also using the fact that the derivative of a sum is the sum of the derivatives. Okay. All right, now we're fairly close to being ready to go. This one requires the chain rule, but I think we're ready to do that one, though. Very similar to the one we did before. This one's okay, I think, too. Except we need to do the little switch thing there, too. So can we handle that? I don't know. Can we do all that at once? So hopefully after all of this stuff we're doing, you'll feel more comfortable to deal with these integral expressions in lots of different algebraic situations. All right, so let's very carefully, who wants to be our volunteer here? Just tell me what I should write.
I can do the one on the right.
Jackson, go ahead.
Okay, so you're just multiplying. Okay, so you put 1 over 2 plus e to the 2x times 2, right?
Yeah. What else do we need there?
Negative.
Yeah. So far, so good. Everyone agree?
Plus, yeah.
Everyone agree so far? Let's stop there.
Wait, isn't it equal to 2? Yeah.
No. Oh, that's what I said. Is it not? Okay, I might have misspoke.
Okay, my might
Thanks for
misheard.
correcting me, Peter.
I might have misheard. Now are we okay? Let's stop there. Everyone okay so far? Okay.
Okay.
We'll let Jackson keep going.
Then plus the derivative of that, which is 2x. So 2x over
Good.
2 plus e to the x squared.
Brilliant. And I don't think that we're ever going to have a problem that has more stuff going on it than this one does, right? We got the chain rule happening, we've got the split up, we've got the flip, we got it all. This problem has it all. So if you understand what just happened there and why, then like today's lesson mission accomplished. Johnny.
Where did you get negative?
Jackson.
Okay. So
Is where I got it from.
do you understand the reason we made it negative? Because you see
Yeah,
it's
you get
from
the negative?
2x 2 0 up there. So we made it negative to fix that and flip it. Then you get the negative 2 because the derivative of that is 2. So you multiply it by 2 and then
So
negative 1.
just like over here, you should really have the same question, where did the 2x come from? Do you have that question too, Johnny? Okay, well, if you don't have a question there, you're not allowed to have a question about this. Because the answer is, it's the same thing, right? The derivative of x squared is 2x. The derivative of 2x is 2. Right? So it's for the same reason. Alright, so homework from the book tonight. Hopefully everyone knows what that is. How do I stop it?